Welcome to question 1 of paper 2 of the Higher Maths exam of the Leaving Cert 2008. Okay, part A. A circle with a centre minus 3, 2 passes through the point 1, 3. Find the equation of the circle. Well, we need to have the standard form of the equation of a circle in our heads. Okay, it's x minus xc squared plus y minus yc squared is equal to r squared, where xc, yc are the coordinates of the centre and r is the radius. In this question, we are given xc and yc, so that's good, but no radius. Of course, it wouldn't be a problem otherwise. But we are given a point on the circle, and the distance from that point to the centre must be equal to the radius. So we need to know how to get the distance between 2 points, and it's the square root of x2 minus y2 squared plus x2 minus x1 squared plus y2 minus y1 squared, which in this case, if we plug in our values for the centre and the point lying on the circle, we get 17, the root of 17. So this is our radius. We can now plug in values into the standard form of the circle now that we have our xc and yc. And we plug in those values into the standard form. We do some expansion and simplification, and we get x2 plus y2 plus 6x minus y4 is equal to 4, which is the requested equation of the circle. Okay, part B, section 1 now. Prove that the equation of the tangent of the circle x2 plus y2 equal to r squared at the point x1, y1 is x times x1 plus y times y1 equal to r squared. You should be able to recognize the circle's equation as having its centre at the origin. You can make a time-saving conclusion from this, which is that a tangent will be perpendicular to a line from the origin to a point on the circle, which all means that if we find the slope of the line which connects the point to the origin, the tangent must have a slope equal to the negative reciprocal of this line. Once you have the slope of the tangent, then it's just a question of plugging in values into the standard equation of a line to get the requested equation. The slope of a line from the origin to x1, y1 is equal to y1 over x1. The inverse reciprocal of this is minus x1 over y1. So that's the equation. That's the slope of our tangent. So we use the equation of the line, which given a slope and a point is y equal to m being the slope times x minus x0 plus y0. So we take x1, y1 to be x0, y0. We plug in minus x1 over y1 to be the slope, and multiplying across by y1, we get y times y1 is equal to minus x1 times x minus x1 plus y1 squared. Expanding and bringing x1, x2 to the left, we actually are left with x1 squared plus y1 squared on the right, which, according to the equation of the circle, which we're given in the question, is equal to r squared. That's it. We've shown that x times x1 plus y times y1 is equal to r squared, that being the equation of the requested tangent. Okay, we move on to section 2 of part B. A tangent is drawn to the circle x2, y2 equal to 13 at the point 2, 3. This tangent crosses the x-axis at k0. Find the value of k. In section 1 we got the equation of this tangent, and we can see that 2, 3 is the x1 and x1 which we used last time. From the circle equation we also get 13 to be the squared radius r squared. This way we can get 2x plus 3y equal to 13 as the equation of the tangent in this case, but k0 must satisfy this equation as well, so we plug it in, noticing that the y term goes to 0, so the answer pops out fairly easily by dividing by 2, and we get that k is equal to 13 over 2, which is 6.5, and that finishes part B of this question. A circle passes through the points A, which is 8, 5, and B, which is 9, minus 2. The centre of the circle lies on the line 2x minus y minus 3y minus 7 equal to 0. Find the equation of the circle. Okay, for the equation of the circle, whose standard form was given in part A, we need to find the centre and also the radius r. Now when a circle passes through 2 different points, those points have to be the same distance from the centre of the circle. Because we're not given the exact centre here, it's best to start by giving it at least a symbol, so we'll call it xc, yc. We can use the distance formula on both points and let them equal each other. The distance formula for any pair of points, x2, y2 and x1, y1, is, as we've more or less already seen, x2 minus x1 all squared plus y2 minus y1 squared, and the square root is taken of that sum. We will show that the distance formulas of these 2 points from xc, yc equal each other. We can immediately square both sides and we plug in the values for x2, y2, in this case is 8 and 5, and then we let it equal the distance formula when x2, y2 is equal to 9 and minus 2, 9 minus 2. So we expand those values out. It's an equation in terms of xc and yc, and we simplify a little. It may look intimidating, but there are convenient cancellations. In fact, all the square terms cancel each other out. So we can cancel those square terms out, and we get as shown, which we simplify a little, and eventually we get that 4 plus 2xc minus yc is equal to 0. It's an equation, as I said, in two unknowns. But we know that xc, yc also satisfies the line equation which it is on, so we can plug it in there. And then we get 2 times xc plus minus 3yc minus 7 is equal to 0. So we get xc in terms of yc, as shown, which is something we can plug back into our distance formula result to get, once again, as shown, that 11 minus 11 yc is equal to 0. So that implies that yc is equal to 1. This in turn gives us our xc to be 5, which when we plug back into our expression for xc in terms of yc, which we can also calculate the radius by plugging in this value for xc, yc into either of the distance formulas, doesn't matter which. So we plug in, so we get 8, so we use the first point, 8, 5, and we get 8 minus 5 squared plus 5 minus 1 squared equal to r squared. And we get 3 squared plus 4 squared equal to r squared, so we get r, the radius, being 5. So we can use the standard equation of the circle to plug in our values for the centre of the radius and the radius. Okay, that's the standard equation. We plug in 5, 1 as xc, yc. We get r is also equal to 5. So we do some expansion on that equation and some simplification, which is not entirely necessary, but it looks neater. And we eventually get our equation to be x squared plus y squared minus 10x minus 2y is equal to minus 1. Okay, so we move on to part C2, section 2. This is the last point, the last part of this question. A circle passes through the points as given. It's the same circle with the same 2 points. And we have to show that a point P on the arc AB, on the major arc, we have to show that the angle is 45 degrees. APB is 45 degrees. If we're able to remember a certain geometric theorem, this question is made very straightforward. The fact that the theorem is that for 2 points on the circle, the angle subtended by both on the centre point is equal to twice the angle subtended on the major arc of the circle. Subtended is a trendy way of saying made. So the angle subtended on the circumference is 45 degrees, we're told. Then the angle subtended on the centre must be 90 degrees. In other words, a right angle. So that means that the lines made by the 2 points onto the centre must be perpendicular. And in turn that means that the slope of these lines must be the inverse reciprocals of each other. So we need to deal only with slopes now. So let's get the slope of the line connecting A, 8, 5, and the centre, which we found in section 2, which was 5, 1. The slope of the line with 2 points, x1, y1, and x2, y2, is y2 minus y1 all over x2 minus x1. So the slope of AC, which is the point that connects A and the centre of the circle, is 5 minus 1 over 8 minus 5, which is 4 over 3. Now we get the second line, which is CB, okay, the centre to the point B, whose slope is minus 2 minus 1 over 9 minus 5, which is minus 3 over 4. So the two slopes are inverse reciprocal, so the lines are perpendicular. Following our logic, we could then say that the angle subtended on P, that's APB, is equal to 45 degrees, which brings us to the end of this question.